So I'm going to talk today about the computational fluid dynamics, and so first lecture will be very general on what is CFD, how you can do that, what are the different things you have to take care of, and then I'm going to talk about the application of CFD to multi-phase flow and to suspension flows. Okay, and then we'll give you some examples. Okay. So what is computational fluid dynamics? Okay, so these are some examples of simulations of the flow around objects. So the idea, let's say that you want to predict what is the flow and what is the drag or the lift, any forces acting on a spherical particle. So you have seen that during the lectures, you may find some information coming from the theory, so like the Stokes solution of the flow around a spherical body at very low Reynolds number. We have seen also that you can do experiments, okay, and we see the flow and the wake behind the sphere based on visualization. Okay, so these are the two scientific tools which has been used over many years in the past. And since we have computers, now there's a new technique which is doing simulations. Okay, so we can try to use a computer to solve the equations we believe are containing all the physics of the phenomenon. Okay, and this is what is computational fluid dynamics. It's actually we believe that the Navier-Stokes equations are a good model of the flow of the fluid flow. So if we solve the Navier-Stokes equation, then we can obtain the flow solution, okay, the flow evolution around any object, and why not around a spherical sphere. Okay, and this is what you see here actually. So you see a small sphere, and around that sphere you see a mesh, and based on that mesh we are going to solve the Navier-Stokes equation, and then you will get, as in an experiment, the flow field around that body, and based on the flow field we can extract everything. We can extract the pressure, we can extract the shear stress, and from that you can extract the force. Okay, and this is what has been done over the last 20 years to develop new techniques, numerical techniques for solving the Navier-Stokes equation, and this is what we call computational fluid dynamics. Okay, so it is a new tool for making sciences. And then you can compare that with some experiments, with some theory, and you may have agreement, disagreement, and we are going to discuss about that. So the idea of numerical simulation is that you are going to take your equations and then you are going to use numerical technique to get the solution of that equations. So usually you do numerical simulations when the equations are very complex, very tough to solve on the paper. So that could be solutions of ODEs, because many of them don't have any analytic solution, but very often this is what we are looking for are solutions of partial derivative equations, because even if they are simple, you cannot solve them by hand. Okay, so most of the equations which are related to simulations are related to partial derivative equations like the Navier-Stokes equation, but of course for the people interested in electromagnetics you have the Maxwell equations, so there are many equations which contain partial derivations, and then it's very difficult to solve. So the idea is of this simulation is you want to obtain the solution of one equation or a system of equations, but these equations are based on continuous variables. Okay, it could be space, x, y, z, it could be time. So of course you are not going to get a continuous solution, you are going to get to obtain a discrete solution. So it means you have to discretize your space, the real space all the time. Okay, so you are not going to find the solution at any time, but just at some time steps or on the grid. Okay, so you have to discretize your equations over the simulation domain, and of course when I talk about simulation domain, you will very soon understand that you have to give also boundary conditions, okay? Because for all these equations, ODEs and PDEs, you need initial and boundary conditions to define the unicity, to obtain the unicity of your solution. And in most of the simulations, the problems are coming from the boundary conditions, because within the domain, very often the solution is good, but the boundary conditions are very difficult to be representative of the reality. And this is where the problem is coming from, and then it will contaminate the solution inside your domain. Okay, so this is the trajectory that you can follow to solve a problem. So let's say you want to solve the flow around the car. So this is the problem you want to study. So you need a model first, okay, because you want to know the flow, but if you don't know what are the equations which are going to control the physics, you cannot do anything, okay. So you need a model. So the model, for example, for computational fluid dynamics is the system of equations of Navier-Stokes, okay. So this is the model we want to solve, and we believe it is a good approximation, it is a good prediction of the real flow. In some way, you may think it's not correct, because, I don't know, if you, for example, take the Navier-Stokes equation for incompressible fluid, and then you increase the velocity, at some point you will see compressible effect in the reality, but if your model doesn't contain this effect, you will solve it maybe properly, but you will not get the right physics, okay? So you have to take care about the model you solve. If you want to compare to an experiment, you have to be sure that both of them are adequate, okay? So this model in physics, it is based on mathematics, so you have big equations. So for us, that would be the Navier-Stokes equations, and you may obtain an analytic solution, okay? Sometimes, if the flow is very simple, so for example, if you have the flow in a pipe, you may, and the flow is laminar, you may get the analytic solution. The quad flow, there are some examples of flow that you can solve analytically, and this is very important to have some of them, because that will you will use them as a benchmark, okay? So at some point you will make your simulations, choose your algorithm, define your domain, but if you just run the simulation but you don't know what you expect, that will be very difficult to know if it is accurate or not accurate. Because if you compare straight to an experiment, you will see, of course, discrepancies, but you will never know if it's because the model is not correct, your computation is not correct, or because the experiment is containing some errors, okay? So at some point it's very important to get some analytic solutions, so you can compare the solution of your discretized solution to something which is, of course, correct, okay? So based on these equations, you are going to discretize. So this is what I did here. So you see, you start with your car, and then you see the mesh around your car, and of course you are going to mesh all the domain which is around your car where the gas or the air is going to flow. So you transform your system of equation into a discrete problem, and then you are going to solve that with a computer. Okay, so you have two different techniques that I'm not going into the details of the numerical techniques, but I'm going to give you the names at least. So you take one, or you pick one of the numerical techniques to solve the system of equations which has been discretized on your mesh. Okay, and then you get the numerical solution of the discrete problem. And of course the question is, is this problem a solution of your system of equations? Okay, so at some point you need to test if when you refine the mesh, so it means you make the mesh grids smaller and smaller and smaller, do you converge to the continuous solution? Okay, and this is when you need some exact solution of a simple problem. Okay, because here you will get the solution only at some points, and here you get the solution which is valid everywhere in space and time. And the idea of this discretization is, if you make the mesh very, 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 very fine, you should converge with a solution which is mesh-free, which is the continuous solution. Okay, so this is one of the first steps of CFD, is to check that your numerical algorithm, your code, your software is able to give you convergence, to be sure that you are converging to something. And then you have to test if this solution is the correct one on some analytical solution. So you can check what is the error and the rate of convergence. Okay, so CFD is now a tool for researchers and for engineers. It has some advantages and disadvantages. Okay, so for research, you are going to test mathematical models that will be used to try to enhance your understanding of the physics, because you can do very simplified model where you have, or let's say you have a very complex industrial problem, but you say, okay, it's too complex, I cannot understand anything, so I'm going to pick up only one of the phenomenon. So for example, I want to look, so let's say you have a process where you have mixing, where particles which are colliding, you have many things, so you say it's too complex, I'm going to take one of the phenomena and then I'm going to look at that precisely, and then I will give back to the engineer some information that maybe they can use to optimize the process. So for a researcher, it is a use, the use of CFD is mainly for understanding the physics based on simplified problems. Okay. For engineers, the objective is different. Usually they use CFD instead of experiments, because making an experiment is very expensive. It might be difficult. The operating conditions might be also very drastic. For example, if you have a process at high temperature, high pressure, that could be dangerous. Okay, so using CFD, if you know how to use that, if you are careful, if you have a good software, you can you can reduce the number of experiments. Okay, and then you can also have an idea. For example, if you have a process and you say, I would like to know if I change the entry, I change the geometry, does it optimize or not my process efficiency? So you can test some ideas. Maybe you are not going to get to obtain exactly the right answer, but that will give you at least the trends, and then you can avoid to do some experiments. Okay, so usually for engineering people, the use of CFD is to lower the cost of experimental investigations and then test new ideas without making experiments. And then at some point, when they decided that this is a good way to go, then they do the pilot and then they test. Okay. So there are advantages, disadvantages. One advantage is that it's quite easy to use. So actually you may think that doing CFD is simple. You take a software like Fluent ANSYS. There's many buttons where you can click, you select things, and at some point you get a result. You will always get a result. It could be wrong, but you get a result. Okay, so this is the advantage. It's quite easy to use. You can modify the parameters. You can say, okay, I'm going to change the velocity, I'm going to change the density, I'm going to change the viscosity, and then you get many information. Okay, so it's not very expensive. Depending on the type of simulation you want to do, it's not very expensive. You can run it on a laptop, you can run it on a workstation with few processors. So compared to an experiment, it's very less expensive. Okay, but of course, there are some disadvantages, and the first one is what I told you. The first one is that you get results. Any time you do a simulation, you get something, and 95% of the time it's completely wrong. Okay, so you get a nice picture, you get some colors, but you think it's correct, but actually it's not. So this is what we give some other names to computational fluid dynamics. So it could be called colored fluid dynamics, because you think you are doing fluid dynamics, but actually you are just painting. Okay, you don't just choose colors and make things. So it is nice for advertisement. If you make a brochure, that could be nice, but it is probably wrong. And the last one that you don't see at the bottom, it's colors for direction, the colors for directors. Okay, so you have your boss, and you say, okay, I did a nice study. Look, I have this result, and then you make a movie, it's moving, so you can think it's correct, but actually it's completely trash. Okay, so this is the main advantage. The main disadvantage is that you will get many information, many results, and you may think that this is correct, and you may think that this is what is going on into your pilot plant. Okay. So be careful about that. So I told you you have to select a way to solve the equations. So there are many different types of methods. So I give you the name of a few of them. So the first one which has been developed is what is called finite difference method. So it means you take your equations, your PDEs, you have a mesh, which means you are going to look for the solution at some points, and you are going to use the Taylor expansion to approximate the partial derivative equation. So it's very simple. So you take, for example, a mesh. Okay, so let's say that here you have x1, here you have x2, here you have x3, x4. So the distance between 2 points is delta x. And in the equation you have somewhere in your PDE, you have somewhere df by dx. Okay, somewhere you have a partial derivative over x. So the idea of the finite difference method is to say that you can make, for example, a Taylor expansion of the value of f at x2. So it will be f at x1 plus x2 minus x1 df by dx. Okay, and then you are going to approximate this by f x2 minus f x1 over x2 minus x1. Of course, you have many terms here. Okay, so the finite difference method, this is the basic idea. You do a Taylor expansion of your terms, so it could be first order, second order, third order derivatives. You make a Taylor expansion, so at some point, if you need the second order, if you need the second order derivative, you go to the next order. You will see the second derivative at the point you need. And then you make some algebraic operations to extract the partial derivative you need in your equation. And then you place that into your system of equations. And at some point, you have transformed the partial derivative equations which are continuous into a set of algebraic equations. Many algebraic equations that you have to solve together. So this is why you are going to use a computer. Okay, so this is the finite difference method. That was the first which has been proposed to solve PDEs and to do computational fluid dynamics. Then you can, this method is very popular for fluid mechanics, so finite volume method, because in the Navier-Stokes equations are based on balance. Okay, it's momentum balance, mass balance. If you have transfer of heat and mass, you have heat balance, mass balance. Okay, so you have always balance. So it means these equations are based on a balance between the quantity which is entering in the domain or in the cell, going out from the cell, and the rate of evolution inside the cell. And the finite volume method has this property to manage the balances, because you do, instead of looking at the value of your system at one point, you are going to integrate over a very small volume all the different fluxes, the flux which are entering, exiting, and the rate of variation of your variable inside the mesh. Okay, so finite volume method is very popular for fluid mechanics, for CFD, finite difference as well. Finite element method is not very popular in fluid mechanics. It is very popular in solid mechanics. Okay, so if you do deformation of solids, then you will find many codes which has been developed with this finite element method. Okay, so it means you are going to mesh your structure, your object, and then you are going to deform that based on the equations for solid mechanics. But you will not find many CFD softwares based on finite element method. And then you have spectral methods. So these spectral methods are based on the projection of the solution on the basis. Okay, so for example, one of the very well-known bases is a Fourier basis, if your solution is periodic. So you are going to take advantages of the mathematical properties of these functions. So for example, if they are orthogonal with each other, so you are going to take care of that, to take advantage of that, to simplify the set of equations that you need to solve. Okay, in terms of mathematics, that one is a bit stronger. Okay, these two in terms of mathematics is very simple. You see, basically this is what you need for finite element method. For finite difference method, for finite volume, you need to do integration. So you need to know the theorem that we already used, which is the Gauss theorem, which is going from flux to divergence. If you know that, you can do everything. Finite element method, you need to know some theorems of mathematics which are related to weak formulation of integrals. And for spectral methods, then the background in mathematics need to be a bit stronger, because you need to know how to manipulate these Fourier, Chebyshev, and Legendre series. It's a bit stronger, but it's very efficient. It's very these codes are very precise and very fast. Okay, so as I told you, when you do CFD, you will get nice pictures, nice colors. The question is it correct or not? So what are the possible errors that you can do or that you can find in numerical simulations? So the first error might be the physical modeling, okay? Because if your set of equations is not representative of the reality, you may solve it very precisely, very correctly. If the set of equation is not the good set of equation for your problem, of course, this is meaningless. Okay, so for example, if you want to look at the flow around an hypersonic plane, where compressibility of the gas is very, very important, and you take the Navier-Stokes equation for an incompressible fluid, you are going to solve it very precisely, but the solution is wrong because you select the wrong model. Okay, so if you don't take care about the mathematical modeling, the equations, and the range of validity, the assumptions, of course, CFD is not going to give you the right answer because you are not solving the good system of equations. The second source of problems is the numerical scheme. Okay, so all these methods, they have advantages, disadvantages, and you have many choices. So actually, even within one method, you have many different schemes. So it could be first order, second order. You can make it centered, not centered. So there are many choices. Okay, when you want to develop a code, you start to think it is simple. You go like this, but actually, if you read a book of applied mathematics, you will see that you have many choices, and these many choices, all of them have advantages and disadvantages. So if you don't understand what are the advantages and disadvantages, you are going to pick one randomly. So at some point you will get something, but you don't know exactly what is the accuracy and what is the stability of your solution. Okay, so accuracy, stability, convergence, you may also have problems, because if you make a very coarse mesh and you want to know the physics of very small structure, you are not going to capture that. Okay, so stability, accuracy, convergence, these are the three main sources of error. And then you have the errors coming from you, from the developer or from the user. Okay, so you have the right set of equations, you have very carefully selected the algorithm, it has been very well chosen, the applied mathematicians have done a very good job with that, but then at some point you have to write the code, okay, and you know, I don't know if you already wrote some codes, at some point you forget you switch I and G, you switch K and T, you forget one line, you did not define one variable, so you know that you can make bugs, okay? So, and this is the same for all the people, so you have to know that commercial software has been written by humans, okay? So they did errors many times. Sometimes you don't know, but they did, okay? So you can have errors coming from the writer, and you can have also bugs coming from the user. So again, let's say the code is perfect. You never know, but let's say it is perfect. But at some point you will select some options, and then you make a wrong selection. You take this option with that option, but actually it is completely contradictory. You cannot use them. But you did it. And then you get the wrong answer. Okay, so you have many sources. So you can have bugs in the code. You may make wrong choice for the models or for the schemes. You may also use it not correctly when you post-process the data. For example, you want to see the velocity, but actually you plot the pressure and you think it is the velocity, so it's completely wrong. And you have also problem coming from the boundary and the initial conditions and the post-processing. Okay, so when I was a student and I started to learn how to do CFD, so my professor very often was telling us, be careful, you know, the error is very often between the keyboard and the screen. So you know who is between the keyboard and the screen, the guy who so be careful. Very often you are making the error. The code is okay, the equations are okay, but you are making the error. So be careful. Okay, so why do we use computational fluid dynamics? So why in fluid mechanics? Okay, why it has been very popular in fluid mechanics? It's because the Navier-Stokes equations and the equations related to fluid mechanics, like heat and mass transfer, they are very complex. Okay, it seems that they are simple when you look at them, or maybe not, but they are very complex because they contain different ingredients that, in terms of mathematics, make them complex. Okay, so you see that they are, if I have to give some terms to qualify these equations, to characterize these equations, you see that you have, of course, there are PDEs, so partial derivative equations. There are second order, because here you have a second order derivative. They are 3D, three-dimensional, because the flow is very likely three-dimensional. They are time dependent. They are nonlinear because of that term, so you have the product of u by u or u by its derivative. They are dissipative because of that. And in terms of mathematics, I don't know if you know the classification of PDEs, so you have elliptic, parabolic and hyperbolic equations, and actually in the Navier-Stokes equation you have everything. So they are not from one of these families, these three families, they are part of the three families. Okay, so because divergence of u is elliptic, du by dt and that term, these two terms, this is parabolic, and this term is hyperbolic. Okay, so you have everything inside, all the different types of equations of mathematical equations. It is inside the Navier-Stokes equation, so you have all the problems coming from these equations. And these equations are coupled together if you want to solve heat and mass transfer. So you see that at the end you end up with 1 plus 3 plus 1 plus many equations. At the end you may have 10 equations to solve together, and they are all coupled. Okay, so you have so these equations are very complex. You may find some other equations which are complex. For example, the Maxwell equations also are very complex if you want to predict the electric and magnetic fields. It's also very complex. Okay, so as a summary, so what is CFD? You want to solve a problem of fluid mechanics. So you have your equations. You are going to mesh the domain. Okay, so you are going to discretize the space and time into small cubes, into small time steps. Then you are going to code these algorithm, this set of equations, discretized equation, algebraic equation. From that you will get many numbers. Okay, so you have to do post-processing, and from this post-processing you will have an idea of the flow, the heat and mass transfer in your industrial problem. Okay, and at the end you try to analyze what is the physics of your problem. So it's an example here with cyclones and with a process. Okay. So the question is, what do you do with these solutions? So there's a very nice citation from Einstein about the first two tools that we use in sciences. So the theory and experiments. Okay, so Einstein was saying that no one believes in the theory except the scientists who made it. okay? Because sometimes it seems to be very, very ugly, very complex, but the guy who did the theory is confident in what he did. Everyone believes in an experiment because this is reality, this is an experiment. But actually the guy who did the experiment, he knows. He knows that there was a leakage. He knows that the probe was not properly calibrated. He knows that when he was doing the experiment, actually the pump was shaking. So he knows everything. So many people when you look at paper and you have data points of the experiment, you say, okay, this is the reality, this is the target, this is what I have to explain. But actually there are many, many, many problems, okay? So the question is, what about CFD? Do we believe, don't we believe that? Well, this is, you have to make your own, make your mind about that. So is it useful for fluids engineering, for research? Is it useful? And it is, but if you make it very properly, if you do random things with your code, selecting options and just looking at pictures, that's useless, okay? So is it a real scientific tool to investigate fluid mechanics, fluid engineering? So why it has been developing so much? It is because of the increase of powers, the power of computers. Okay, if we were staying like in the 50s or in the 60s with very slow computers, then CFD would not be very popular because the equations that we solved in that time were very simple equations, like ODE is very simple equation. Okay, so here you have some pictures of what was a computer initially and what is now. So now it's like big storage with lights, and so it's very, very clean, very nice. And of course the capacity of calculation has been expanding a lot. So so this is a history of computers, but you see here the increase of the power, the computing power of the machine. So this is the top 500. So here you have the best machine, and then you have the average, and then you have the number 500. So every month, if there's a specific, I don't know if I gave, no, I don't give, there's a specific website where they are collecting all the information about supercomputing centers, and they give a ranking. So every month it is changing. So the first one, if you wait a month, then there will be a new one which is more powerful. And to give you an idea, so you see that my laptop, in terms of CPU, in terms of number of operation that could be done during a second, it is comparable to the best. So number one is red. So it was comparable to that computer in the 90s. Okay, so you see my laptop corresponds to the best computer about 20 years ago, and then it has become expanding. Okay, so there is an increase of computing resources, and most of them are parallel machines. So it means that when you are going to run the code, it's not going to run on just the processor of my laptop, but it's going to be spread over many processors that are going to work together to give you the solution very quickly. But to do that also, you have to you cannot stay just a fluid mechanicist. Okay, you cannot just stay a physicist. You have to learn a lot about applied mathematics for the algorithm, for the coding, and for using all these CPU resources. Because I told you, okay, you have to use many processors, but it's not obvious to use many processors, because some processors are going to do some calculation, but they need to contact the other processor because they need some information from the other processor. Because, for example, let's say that you are going to do a simulation like this. So you do your mesh. So you make your mesh like this, and the idea of parallel computing is to spread your calculation over different processors. So one processor is going to calculate the points here, another one the point here, another one here. Okay, so this is the idea. You have a domain with many grid cells, and you are going to assign to different processors the job of calculation related to each subdomain. And you expect that if you divide by 6 the domain, then you divide by 6 the time of computation, because 6 processors are going to work at the same time. But in fluid mechanics, you cannot solve the problem here without any information of the solution here, because the fluid flow which is coming from here is going there and there. Okay, so you see that you have to send information, to broadcast information to the different processors, and it is done. So you have to code that, and you have to make it properly, because if you solve that problem, and they are completely disconnected, well, it's meaningless. In the fluid, when you have a fluid flow, the fluid is moving everywhere. Okay, so you need to know a bit more about applied mathematics for the algorithm, but also to handle these new machines, which are called parallel machines. And then you have to learn how to learn about high performance computing. Okay, but if you know how to do that, or if you buy a software where some people did that, then you can handle very complex geometry. So I give you here some examples. So this is here a process where you have many things inside. You can make geometries like this. You can look at the flow around many particles. So you can do very complex things. Okay. But still, we have some limits. Okay, so with CFD, you cannot do you cannot simulate all the complexity of fluid mechanics, and more specifically the turbulence. So I give you just a brief introduction to what is turbulence, but you understood that turbulence is composed of many vortices. Some of them are big, some of them are small, and this is the main difficulty in computing turbulence, is because you need a domain which is large, the size of your container, because you need to solve the geometry. If you have a square or a circle, of course the flow will be different. So you need a large domain, but if the flow is turbulent, the Kolmogorov scales are very small, and you need also to resolve. So you need to have grid points with delta x similar to the size of the smallest eddies. Okay, and if you have very small grid and a big domain and large domain, then you are going to end up with billions of grid points, and that will be very, very time consuming to get the solution. Okay, so this is it's very simple to understand, but still we don't know how to correctly model turbulence. Okay, so because it is multi-scale, okay, from large to small scale, so in space and time. So turbulence, multi-phase flows also is very complex, because you may have in your system very tiny particles, and if you want to know the flow around that particles, you need mesh, and these particles are moving. You have billions of that particles, so it's still very complex. Also, the system might have very broad time scales. So let's say that you are starting your pilot plant, so it will take maybe 1 day to reach the steady state, because everything is difficult to. But in your system, you are you have events which are very quick, very rapid. So you have to take care of these small time scales, but over a transient which is maybe a day. So that will be huge amount of calculations. And then you have also many questions about the models that you have to use, because when the process is very complex, you have many physics, many parts of the physics which are all together connected, coupled, and sometimes you don't know exactly what is the physics. So for example, there are many problems when you have heat and mass transfer. You don't know what is going on the interface. Even when you have chemical reaction, okay, there is a chemical reaction, but what is the kinetic model that you are going to use? What is the rate of production of your material? So there's still many open questions about even the model that you have to use. And if you don't know the model, of course, you cannot make the CFD. Okay. Okay. So very often the key point is the choice of the modeling, because if you make a wrong choice at the beginning, then the rest will be for the trash bin. Okay. So I'm going first to to talk about that. Okay, I'm basically going to talk about the 2 points, 2 items, turbulence and multi-phase flows. Okay, so I'm going to try to explain you why it is so complex to simulate a turbulent flow, and then I will move on the simulation of multi-phase flows with particles, which is the topic of the lectures. So you remember that slide where I told you that in a turbulent flow you have large eddies related to the size of your container. So let's say you have a tank. In that tank you have an impeller. This impeller is going to generate agitation, so it's going to generate very large vortices of the size of the tank. It's going also to fix the energy input into the system. And then you have the Navier-Stokes equations, which are going to break these big vortices into smaller eddies, following that evolution, k minus 5/3 proposed by Kolmogorov. And at some point, the vortices are so small that they are going to dissipate energy due to shear, due to friction, like here, but the fluid is, there is friction between the fluid elements, and then you dissipate the energy, and you have to dissipate all the energy which is coming from the large scales. Okay, so because at some point you reach a steady state, so the energy that you input has to be consumed somewhere. Okay, so that will be fixing the Kolmogorov scale, and then you have to try to do the CFD of that. So we can evaluate what will be the mesh grid. Okay, so the idea is we have a turbulent flow now. So we have a turbulent flow. So let's say this is, okay, so this is your container, your tank. Inside that tank, so you will have big vortices, okay, of the size almost of the container. And then you have also, so this is what I call L. So this is the length of the big vortices. So it is in some way related to the diameter of your tank. Okay, so L is comparable to the diameter of your tank. And then you have the smallest eddies, the Kolmogorov scales. Okay, so you have these smallest eddies like this, many points. Okay, and this is eta. Okay, so and if you want to do a very precise simulation, you need to mesh the container with many grids, but you need to mesh also that one. So if I make a zoom, okay, I take this as a zoom. So I take one of these small eddy, so it is now that big. If I want to represent that correctly, I have to mesh it as well. Okay, so I need maybe, I don't know, with let's say a grid like this. Okay, with a grid like this, within that vortex, I will have 4 or 5 grid points. That's enough, you know, to capture all the flow structure, the flow field of that. That's very small vortex. So you see that I will have grid points like this, and I need to mesh the whole domain. Okay, so now we are going to try to evaluate the number of points we need. So we can evaluate that theoretically based on the by using the Reynolds number. Okay, so the Reynolds number is based on the large scale. That will give you an idea if the flow is turbulent or not. Like in the Poiseuille flow, you are going to base your Reynolds number on the mean velocity multiplied by the diameter of the pipe divided by the viscosity. So here U is the velocity at the large scales multiplied by the length of these large scales, so U multiplied by L divided by nu. So we can estimate that using these equations, and then what we see is that the ratio in terms of size between the Kolmogorov scale and the large scale is evolving like to the Reynolds to the power minus 3/4. So the mesh grid is going to evolve like L over eta to the power 3, because of course you have 3 directions, okay, so it's why it's to the power 3. You are going to mesh in the 3 directions because the vortex is maybe moving in the 3 directions. So that will give you an idea of the mesh grid, but in terms of computing time, you have again another source of time computing. It's the time step, because when you have very fine mesh, the time step, the time scale of these small turbulent eddies is also very, very small. So you need to have a delta t, which is also adapted to delta x. Okay, and that will give you at the end a computing time which is proportional to the Reynolds to the power 3. And it is very, very, very drastic, because if you multiply by 10 the size of your container, so let's say that you make a lab scale experiment which is about 10 centimeter, and then you do the CFD of that, you compare with your experiment, and then you are okay, you find it's good. But you want to go at the pilot scale, so you are going to multiply by maybe 100 if you go from 10 centimeter to 1 meter. So you multiply by maybe 100. If you multiply by 100, that will be 10 to the 6. So the CPU time will be multiplied by 10 to the 6. So maybe it was when you did the simulation of your small tank at the lab scale, that was maybe 1 week of simulation on your laptop. Then that will be 10 to the 6 week. So this is a problem, because 10 to the 6 weeks you will be completely dead, and your children will be dead, and the laptop is still running. Okay, so so it's completely unfeasible. Okay, so you are going to say, okay, instead of my laptop, I'm going to use a very big computer. So I'm going to use maybe 100 laptops, 1,000 laptops, but still, even if you have 1,000 laptops, so from 10 to the 3 to 10 to the 6, that will be again 10 to the 3. So 10 to the 3 weeks, again, your children and the next will be dead. Okay, so you see that it is completely unfeasible. So to give you an idea, if you have a problem, let's say in chemical engineering, but it could be any process, if you have length which are 10 meters, which is very classic in the industry. If you go in any plant, you know the size of the container is very often 1 meter, 2 meters, 10 meters. The speed might be 1 to 10 meters if you are conveying fluids. So the Reynolds number, you see how it's big, how it is big. And if you look at this, and you look at the range, at the length scale ratio here, you will find a huge separation between the large scales and the small scale. Okay, so to give you an idea, I don't know if I have it for the, no, I don't have it. I have an example on a plane. So you know that in Toulouse we are building the Airbus A380. If you want to do the resolved simulation of turbulence around an airfoil, so I mean you want to solve the Kolmogorov scales and everything, for now, so you know the size of the Airbus A380, so it's like, I don't know, 60 meters or very, very big. For now, we are able to solve the flow very properly, like a matchbox which is placed on the wing of the plane. Okay, so you see the size of the plane. By using the best computers, we are able to solve something like 10 centimeters by 10 centimeters by 10 centimeters. At the real speed, at the real Reynolds number, in the real condition of the flight, during the flight. Okay, so you see we are able to solve that big compared to the Airbus A380. So, so the question is, what could we do? Because if I say that to my boss at Airbus, he said, okay, it's completely useless to simulate that part of the plane. You are not going to get any information about the drag, about the lift, about can I optimize the shape of the wings to generate less noise, or I don't know. Okay, so you need at some point to do something. And everything is related to that. So how will I change the model to be able to handle the complexity of turbulence without solving these small eddies, because you cannot avoid to solve the size of the domain. Because if you say to Airbus, this is the Airbus A380, which has it has this shape. Okay, it is not very good at drawing, but okay, so it has this shape like this. Okay, and with the motors here. Okay, so it has this shape. But you say, no, I'm not. This is too complex. I'm going to solve the flow around the sphere. Okay, so your boss is not going to believe you. He asks you to give you he wants from you the flow solution around a plane, and you say, okay, no, I'm not able to do that, but I'm going to give you an answer about the flow around the sphere. That is a very poor, poor answer. So you cannot avoid to solve the flow with its real geometry. Okay, so the large scales, you have to solve them because it is related to your process, to your design, to your object. Okay, so you cannot prevent that. The only thing you can prevent is to solve the small structures, because this is the one that are very time consuming, because you need very small mesh grids over a very wide domain. Okay, so the idea of turbulence modeling is how can we do to avoid the simulation of these small eddies, these small vortices. But the problem is these small vortices have a drastic impact on the flow, because these small eddies are in charge of the dissipation of energy. So it means if you forget to solve these small eddies, the rate of input of energy is the same, because you are going to solve the domain, the size of the domain, the large eddies. So you will sit inside the system, you will feed the system with energy, but you are not solving the scales which are responsible of the dissipation. So it means that you are going to have a mismatch between energy input and energy consumption, and then the solution inside your system will be completely wrong. Okay, so you see, this is the problem of fluid mechanics and turbulence more specifically, is that both the big and the smaller scales have a certain effect on the flow. These ones are injecting energy and controlling the geometry of your flow and the relevance of your simulation. And the small eddies are in charge of dissipation. If you are not dissipating the energy, it will be contained in the rest of the flow, and then the flow will be different from the reality. Okay, so this is really the main problems of fluid mechanics and turbulent flow. So the question is, how can we do to manage this difficulty? Okay, so the first technique to solve the Navier-Stokes equation is the one I described just before. So this is what is called direct numerical simulation. So it means there's no modeling. You just take the Navier-Stokes equations, you do the applied mathematics job by discretizing the equation with finite element method, finite difference, or spectral, any method, but you solve exactly the equation as exactly as possible with the scheme that you selected. Okay, but you don't modify the model. But this is going to give you that limitation. Okay, the limitation of direct numerical simulation is related to the Reynolds number. So you might be able to do the simulation, for example, in a pipe flow without any modeling up to Reynolds 10,000. The problem is in the plant, it will not be 10,000, it will be 100,000, 1 million, maybe 10 million, and then you are facing that problem. Okay? So the second technique is going to take advantage of what I told you. So we are going to look for a technique which is going to resolve the container size, the big vortices, but you are not solving the small eddies. Okay, but you have to take care of them. You have also to dissipate the energy, because if you don't dissipate enough energy, then the system will become crazy and the flow is wrong. Okay, and this is called large eddy simulations. Okay, so large eddy simulation, the idea is to split the different scales So from the largest to the smallest, into some of them which are resolved, so you are going to simulate them, and some of them you are not going to solve because that would require too much points, too much grid points. So you are not going to solve them, you are not going to resolve them, but you are going to plug a model that will be in charge of dissipating energy instead of the small scales. Okay, because if now I decide that I forget, I am not able to solve this small eddy, okay, so I will have a mesh, let's say that you have a mesh like this, which is a grid cell which is containing many small vortices. These small vortices are in charge of dissipation of energy, but you are not able to predict the correct rate of dissipation because your smallest grid cell is like this. Okay, so and if you look at the Navier-Stokes equation, so if you look at the rate of dissipation, so epsilon, it can be written like 2 nu EIG. So you remember EIG, this is the rate of deformation of your flow, and this is proportional to U over eta, so U eta over eta. So it's a gradient of velocity. Okay, so the rate of dissipation is proportional to the viscosity. Of course, if your fluid is more viscous, it will dissipate more energy. But it is also proportional to U square, U over eta square. Okay, so it means if you solve a flow with a length scale which is too big, then you will underestimate the rate of dissipation. So the way to compensate that is, okay, I'm going to solve the flow with a grid delta x with a grid which is larger than eta. So the rate of dissipation due to that term will be less than what I expect. So I'm going to multiply that by a viscosity which is more and to compensate. Okay, so and this is the concept of turbulent viscosity. Okay, so at some point you may use a computer, a software, and you will select some models of turbulent viscosity. So turbulent viscosity means I'm going to plug a model which is going to generate artificial viscosity, numerical viscosity, modeling viscosity, which is going to compensate the lack of dissipation because I'm solving the flow with a length scale which is too big. Okay, so you see, if delta x is larger than eta, that will be smaller than what you expect. So you multiply by a viscosity which is larger to keep the good rate of dissipation. Okay, and then if you have you still have the good input, if you have now the correct output, then your simulation has more chances to be correct. Okay, so this is the idea of large eddy simulation, is to split. So let's say that this is your distribution of energy over the length scales, so from the large to the small. There is a threshold corresponding to your mesh grid, and all the small scales you are not going to solve them because it's too costly in terms of CPU, but you are going to use a model which is going to dissipate energy. Okay, so you have resolved scales, and then you have what is called a subgrid model, which means that you are going to use a model for what is inside the grid to compensate the rate of energy consumption. So it will, of course, it will save CPU because you will need less mesh, less grid points. It will save CPU, but it will be a different model. It will be, you started with the Navier-Stokes equations, but now you are not solving the Navier-Stokes equations. You are solving equations which are containing something inside. A new, you have a patch inside for the modeling of this viscosity. And of course, the question is, what is the validity of the model you are going to use, and what is the impact of the model you are going to use on the rest of the simulation, which is your interest. Okay. So in many cases, you can use the theory of Kolmogorov to help you to design this model, because very often, in many cases, the role of the small scales is really to dissipate energy. So it's very simple to model the rate of transfer, and then you can have a good idea of the value of your subgrid viscosity. But in some cases, the flow is very complex. And unfortunately, this is very often the case in the industry. So for example, LES models are very well working for very simple flows, like the flow in a pipe, the flow in a square pipe or a circular pipe, the flow in over a flat plate. So for simple geometry, LES are doing very nice job. So it means if you compare the real solutions with experiments with LES, you have very good agreement. But when you go to complex geometry, the problem is that the theory of Kolmogorov is valid for that kind of flow. A flow within a cube, which is purely homogeneous, completely isotropic, which means there's no direction where the flow is, the average of the flow is non-zero. So the theory is based on a very simplified turbulence. And in many cases, when you have let's say a bend, or you have a cyclone, you have a complex geometry, the flow is no more homogeneous, is no more isotropic, but still you are going to use the only theory which is available to design your subgrid modeling. So you are going to do some errors, and the question is how big the errors are compared to the reality. How far is the turbulence from the real turbulence? Okay, and this is very, very open questions. So this is one approach, large eddy simulations. So this is one approach that you can use. It is indeed saving CPU, but still it is very time consuming. I don't know any industry using that. Okay, even the biggest one, like big companies like Airbus, like Total. I'm talking about French companies. I don't know in India if they are using, but I guess no. Because still it is very time consuming, because you have to solve the 3D simulations. You have to solve, even if you are not solving the very small scales, but you still have to solve smaller scales than the container size. So still it is very demanding in terms of CPU resources, and for now it is only used in research. Basically in research, some people in very advanced research center, industrial research center, they have the capacity in terms of supercomputing centers to do that, but it is not available in all the companies. Okay, it will come at some point. If we look at that, if we look at that, we just have to wait. Maybe in 10 years, in 20 years, maybe when you will be working and you will be a senior researcher or senior industrial people, maybe that will be all the people are using LES because it's much more efficient. But for now, it's not the case. And actually, some people I have a story about that. So when you do the design of a simulation, it's like doing the design of an experiment. Okay, so you are going to evaluate how big will be the simulation, how long it will be to get the result. And sometimes you face a problem that the simulation is so long, like could be 2 years, 3 years, 5 years. Is it worth to start the simulation, or is it better to wait for the next computer which is going to run faster? Okay, so we are going to make a break.